All right, well, Keith is a very tough act to follow. So I'm going to tell you about two things here. One is finding lost cities, or one of the lost cities anyway. That's the romantic part of the presentation. And then I'm going to tell you a little bit something more, in a sense, more interesting for future developments. All right? In fact, all right, so what do we use to find the lost cities? Well, we use Bayesian search theory. And Metron has a lot of background in that. I published a book, Theory of Optimal Search. I've been involved in a lot of successful searches. One for the submarine Scorpion in 1968, the ship of gold that you heard about here in 1988, Air France Flight 447, 2001, and Metron, under my guidance, put together a planning aid for the U.S. Coast Guard for finding people and boats that are missing at sea. That is used every day by the Coast Guard to find somebody. It's a very successful operation. All uses Bayesian search theory. So this stuff works. So I think you've already heard Keith tell you about the background here of Namibia, and I won't go over that. And also the two cities here, Aurania and Sevilla de Oro. So Keith wanted us to use the historical information that was available, which he brilliantly and with a lot of hard work put together to put together probability maps to locate these cities. So here are our goals. Here are our tasks starting in July 2019. First, to produce the probability maps for the lost gold cities. Okay. But second, and more important, I think, for the future, identify areas of high likelihood for the presence of gold, silver, or copper deposits. And I'll tell you how we did that too. So that's going to be looking ahead to the future. So the information for the lost cities, well, that was historical, the maps and descriptions that Keith told you about, some topographical information, and I show exactly how we use that to produce probability maps. Well, just for LaGroix. The information for identifying high likelihood areas for mineral deposits, well, we take all the data, the geological data, geophysical data, geochemical data, and those are worked into, stream chemistry too. Those are incorporated in by expert opinion into likelihood ratios, and that allows us to combine all that data into one single map that shows you location, high likelihood areas for locations of deposit. So that's part two. All right. So the probability maps. Well, we had help. I always have to have help on these. And some experts, like Keith, getting all the data, and Camille helping me review it. So we reviewed the historical accounts that Keith found, and I'll show you what an account looked like there. And then when you look at these accounts, I mean, you have to somehow quantify them. And what you do is you quantify the uncertainties. There's always large uncertainties in these accounts. You have to quantify them into probabilities. These are subjective probabilities. And then you weight the credence of each piece of information in terms of these probabilities, and you combine them in a Bayesian fashion to produce these probability maps. All right, so here's an example. Two pieces of information. Aurania says it's located at a point halfway between Zamora and Santiago de la Montaña. So here's Zamora down here. Santiago de las Montañas down here. So along the Zamora River, so here's the Upano and the Zamora. Where they join is now called the Santiago River, but in the historical accounts they just refer to it as the Zamora River. So that's a point halfway between those two cities. Okay, great. Along the river. How do you use that information? I'll show you. And then the other was, well, the city of Logroño is within half a league of the Zamora. How do you use that information? And how do you combine it? All right. So here's what we did for this piece of information about being halfway between Zamora and Santiago de las Montañas. Okay, so how do you convert this information into a probability density? And the way you do this is, the way we did it, so halfway between Zamora and Montañas. So we said, well, okay, halfway between. What does that mean? Well, probably between 1/3 and 2/3 of the way. So we put 0 probability out of the way there. And then we said, in the middle here, we'll give it the highest probability density, but then we'll drop the density off as it goes toward the sides here, toward 1/3 and 2/3. So this is a subjective estimate of what that piece of information means, put into a probability density in a way, and that the importance of doing that is we can then use it. So how do we use that? Okay, we also had another piece of information within half a league of the Zamora River. Well, a league in those days is about equivalent to 2.5 kilometers now. So we figured that within half a kilometer, well, between 1.5 and 3.5 kilometers from the river. And could it be north or south? Well, looking at the geology, we figured, Camille, again, doing this, figured north is more likely than south. So we give it 0.75 north, 0.25 south. So, okay, these are all kind of subjective, but using expert opinion and quantifying the information and uncertainties by these probabilities. That allows us to put them together. Okay, next. So how do we do that? Well, first of all, we created this buffer zone between 1.5 and 3.5 kilometers around the river. And then we populated that buffer zone with a large number of simulated points uniformly distributed in that zone. How do you do that? Actually, for the computer science geeks here, we have a large number of points. But the way you do this is you just make a uniform simulation of points, large number of points over the rectangle, and you just chop out anything inside of one of these zones here. So you get a uniform distribution over that. Each point is given initially weight 1. Okay, so they're all equally weighted. All right, what happens after that? Well, so for each point in that region, this point S up here, you find out the closest point of approach to the river, and you calculate the distance of that point from Zamora, and put it into that probability density that I showed you before. So that gets the weight P of x, well, 1 times P of x to that point. You do that for each point in that zone. All right. And then, next item. All right, you still got some more information to incorporate. So now each one of these weights, you now multiply that by, if they're north of the river, by 0.75, south of the river by 0.25, and then so you've got a bunch of points in there. You can renormalize them so that they add up to 1. You just take the sum of all the weights on the points, divide the weight at each point by that, and you get the probability of each one of those points. So that each point represents a possible location for Lagrange and weighted by probabilities. So how do we? So we show that further. So for the actual probability distribution is all those points, but to visualize it, we divide it up into cells and add up the probabilities in each one of these cells. And those cells that have high probabilities get a red color. Next is yellow, and lowest is blue. So you can see the probability distribution that we produced that way. Of course, the blue here below is the south part that's low. Up here is high probability. Okay, but we now have another piece of information we want to incorporate. How do you do that? All right, what's that piece of information? Well, there's another description here that says Lagrange was located a short distance from the meeting of the Upano and the Zamora. All right, so how do you incorporate that? Let's go down here.
Probably just use the arrow keys if you want to go to the next page. You want to go to the next page?
No, I want to go just put it down here. Okay. So well, we said, okay, short distance. Well, we'll represent that observation. It's like a measurement. In terms of a likelihood function. And here, we'll say highest likelihood at 12 kilometers, and of course, dropping down to 0 close to the junction, because it was at the junction, was set at the junction, not a short distance from it, and allowed for the possibility that it might be far away too. So that likelihood function was applied to each one of the points. Let's see, we So you multiply the weight of each point by the gamma density for the distance from the junction. And the result was you get this probability distribution, which moved it closer to the junction of the rivers. So okay, this is the resulting probability distribution. A lot of subjective information in it, but it's our best understanding of the information, and we have represented that information in a way that allows us to combine it all into one probability map. So that's how the process works. And the surprising thing to most people, me too, is how often this works. This really does work, folks. And it worked in this case brilliantly, as Keith has already told you. Okay. Well, now, let's go. So that's fun, but very, very few of you are going to have all the information for a lost gold city that you want to find. So, all right, you're probably not going to be able to use our methodology to help you out there. But mining operations have a lot of data. And one of the problems with having all that data is, how do you combine it? How do you combine it in a way that you can understand the meaning of it? Okay, so what we developed with the help of Camille and Richard Spencer was a way of combining all this information using likelihood ratios. And I'll show you how we did that. So, we produced likelihood ratio maps for locations of porphyry, epithermal, and lead zinc deposits. Likely, deposits that would be a high enough quality for commercial exploitation. And here's the sort of information we use: both the lithology, the types of rocks found, magnetic anomalies, stream sediment geochemistry. And for each piece of information and type of deposit, we had the experts weight that information for us in terms of a likelihood ratio. All right, how did they do that? They said, well, suppose there was a deposit of, a porphyry there. What would be the probability of getting that piece of evidence? And suppose they had a porphyry there, and suppose we had no porphyry there, what would be the likelihood of getting that evidence? So, okay, if they're the same, top and bottom, that gives you no information. If the top has a higher probability number than the bottom, that's information. And the higher that ratio, the stronger the information. So it's a way of the experts telling you how strong that piece of information is in terms of a likelihood ratio. And they did that for each piece of evidence in each deposit type. And so for that piece of evidence, if you've got the evidence over a map, that gives you a likelihood ratio at all these points on the map of the region. And you've got a likelihood ratio for that piece of evidence for that type of deposit. Okay, fine. Now then, for each deposit type, hold that deposit type fixed, and you multiply the likelihood ratio maps for all those types of evidence. Multiply them together. And this is a principal Bayesian fashion for combining that evidence. You multiply them all together, and you get one overall likelihood ratio map that tells you, given the evidence that you have, all the evidence you have, where the best locations are for discovering these minerals. Okay, and that's what we did. And this, you can see, this is not unique to the Kukutu project, to the Lost Cities project. This could be used in a lot of different places. So here's an example of what they did for lithology. For each type of rock, and each one of these types of deposits, lead, zinc, porphyry, epithermal, they rated the, if you got the, this Napo formation, how likely is it, what's the likelihood ratio for lead, zinc, porphyry, very low, epithermal, very low. If it's a low likelihood ratio, so it's not likely to be there. So that's information too. And so here, all this information is put together into a set of likelihood ratio maps for that evidence. Here it is for porphyries, for epithermals, and for lead zincs. The only one that really got very, very much positive information here from the lithology was the lead zinc. Likelihood ratio of 1 is about this color here. So you got to get up to the orange or ideally red to get strong indication. Or that's one type of evidence for the three types of deposits. We also did that for porphyries and also for stream sediment data. Now for stream sediment data, you had to do something a little bit different. You said, I'm looking at the chemicals I detect in the stream sediments. What does that tell me? Well, that tells me something about the catchment area. And so you would then assign your likelihood ratio to the catchment area. And what Camille and Richard did was, well, they made up a way of scoring the evidence they got. So here's the pathfinders you could find for epithermal, gold and silver. And they said, well, and they gave, if you found gold, you get a weight of 3. All the other ones, you get a weight of 1. And you total up the number you found, you get a total score as high as 6. Same thing, lead, zinc, and porphyry, copper. Then you would apply that to the particular catchment zone. So you apply that likelihood ratio resulting from these. Well, they went from these total scores to produce a likelihood ratio. So here we are, again, using the expert opinion to tell us how to weight that data, but weight it in terms of a likelihood ratio, which allows us to combine it with the data that we had for the geology and the data that we had for the porphyries. So that's the crucial, that is the strength of this approach. So here's the result here. Well, here are the, here's the results we got for the stream sediments. Now you can see here you get some actually good indications. You get some nice red indications here. For porphyry, epithermals, Keith was telling you about the epithermal down here, and lead zinc. And now, we did a similar thing just for the porphyries too. I mean, just for the magnetic anomalies, I should say. And here's the results here. So here's the porphyry map on the left-hand side here, combining all the evidence. This is all evidence in one map. Here's your epithermals. You can see that you've got all this, just a lot of data, and you now have it combined into a map that tells you likely areas to look. And the map is combining that evidence in a way that's weighted by your experts and combined in a fashion, in a legitimate Bayesian fashion. So this is the power of that method, taking the data, applying expert opinion to it, and combining all the data in a principled fashion.
Larry, I might point out that on the left-hand side, the porphyry, our target of Wacha is up there. And
Up here?
that's it, there.
Yeah.
Yeah. So you guys selected it, a couple of years before we did.
Well, we selected, the data told us.
Yeah.
The data processed through expert opinion and combined in this Bayesian fashion. Okay. And just for the heck of it, we overlaid some of these over these maps. One is a map for Sevilla. Okay, Sevilla's TBD. We don't know where that is yet. I guess we got a little distracted by a piece of evidence that we now would like to take out of that map, which tended to move the map away from this river a bit. But it's Logroño. You can see here these are the epithermal maps laid over the probability map for Logroño. You can see that here it is over here. Here it is over here. You can see where the high probability regions are there. So this stuff actually works. Not only works to find lost gold cities, but also to identify these good areas for the deposits. And just again, you can see where they're finding all the alluvial gold up here. Here's our high probability area for the location of Logroño. Pretty good fit. Very pleased about that. So, never mind this, you're all familiar with this, I don't need to show you that. And Keith did point out to you that the concessions that Aurania has are right above the area where this gold is a little bit washed down, it had to come from somewhere, so those concessions areas are likely where the gold came from. All right, so from our point of view, what do we show? Well, Bayesian search methods proved highly effective once again in locating Aurania, as they have done for the ship of gold that Keith told you about, and also for Air France 447, that flight. And again, Coast Guard using it every day to find people. They're very, lots of success stories from the Coast Guard. So, okay. Bayesian methods, once again, work. These search methods. Now, the likelihood ratio methods here are demonstrated as effective for quantifying information from many sources, incorporating expert opinion, and combining information in a principled Bayesian fashion to produce these one likelihood ratio map, combining all that information for you in a way that you can easily understand what it means. So my contention is this ought to be applicable to many exploration activities, and it should be applicable to companies that have data sitting in their vaults that they have not used or have not looked at. They can go back and look at that data and with expert opinion, put it together to give new information about where they ought to be prospecting.